Edexcel Core Pure, Sequences in Series 3, Method of Differences and the Maclaurin series. The general Maclaurin series. We've previously seen how a function can be expressed as a polynomial. So for example, here if we had a function p of x and we're trying to write it as a polynomial, we look at the function of x and its derivatives when x equals 0. So here when x equals 0 we get a becomes p of 0, and if we differentiate and then let x equal 0 we get b equals p dashed at 0, and if we differentiate again we can find c, and when x is 0 we get p double dashed at 0 over 2. So we can find the various coefficients of our polynomial by looking at the derivatives of the polynomial when x equals 0. If we now start to generalize this idea, we can express a function f of x in the form here. So this is our coefficient a, and here is the coefficient b, and this is the coefficient c. So we need to be able to find our various derivatives of the function when x is 0. Notice that the derivative required, for example here we've got a third derivative, is the one used with x cubed. So if we're looking for the coefficient of the x to the power r, we would need the rth derivative of the function when x is 0. Again, if we look at the x cubed term, the denominator is 3 factorial, and therefore the denominator for the general term will be r factorial. So that gives us the general Maclaurin series of function f of x, and you will find a more formal proof of this in a textbook. We can now use this general Maclaurin series to approximate a function, provided that we can work out the various derivatives of the function when x is 0. If the series converges to a limit, then it is converging towards f of x. And some Maclaurin series are only valid for a certain range. So in this example we want to find the first 3 non-zero terms using the general Maclaurin series of f of x equals cos 2x. It's often helpful to put all your information and calculations you're going along in a table. So for example here we're starting off with f of x is cos 2x, and we've already found that f of 0 is 1. If we differentiate f of x we get f dashed x, and if we put 0 in there we get f dashed at 0 is 0. And we can carry on working out further derivatives. So f double dashed x is minus 4 cos 2x. So we could put that in there, and if we now let x equal 0 we get f double dash 0 is minus 4. If we differentiate again we can use this nice neat little notation for the third derivative. So we get the third derivative of x is 8 sine 2x, and if we find the third derivative when x is 0 we get 0. And just one more, the fourth derivative of x gives us 16 cos 2x, and if we find the fourth derivative when x is 0 we get 16. So by putting all our calculations and derivatives in a table, it allows us to keep things well organized. So it's worth noting that the odd derivatives are given as 0, so there's a first derivative, and the third derivative and the fifth derivative would all be 0, so it's only the even derivatives that are given as non-zero coefficients. And when we sub the 1 and the minus 4 and the 16 into this general Maclaurin series at the top of the screen here, we will simplify it to get 1 minus 2x squared plus 2/3 of x to the 4. If we start to investigate this a little bit further, so for example, if we look at the sixth derivative of x, we will get minus 64 cos 2x, and therefore the sixth derivative when x is 0 is minus 64. So now if we look at the general derivative in this pattern, we know we only need to consider the even derivative, so I'm going to call this derivative the 2r derivatives. So 2r will be an even number, and in order to get these values of 1, minus 4, 16, minus 64, we need minus 4 to the power r. So for example, when r is 1, so this will be a second derivative, we'd have minus 4 to the power 1, which is minus 4. And then we're also going to have a cos 2x. So the 2r derivative when x is 0 will be minus 4 to the r. So we can now generate our general term in this pattern, and our general term in this pattern is minus 4 to the power r to get the alternating powers of minus 4, and then we need an x to the 2r, and the denominator, if you look back, the denominator, remember, was the factorial of the power, so here we're going to have 2r factorial, and that is our general term in the pattern. Just a note there that if you are doing a trigonometric series, then you must always be working in radians. So now we can see a full table of workings, and this general term is the important detail. So we need to create this 1, minus 4, 16, minus 64, and to do that we need minus 4 to the power r, and we need a denominator which is an even number, and it matches the power of x which we are calculating. We can now look at the effect of extending this polynomial approximation using a GeoGebra file. So here n is 2, so this is representing a quadratic approximation for cos 2x. So the green graph is cos 2x and the red one is our quadratic approximation. Notice when I go to n equals 3 it makes no difference because the coefficient of x cubed would be 0, but when I go to x4 we get a quartic approximation for cos 2x, which is slightly better, and as we improve the order of the polynomial, so now we're up to an order 8 polynomial, and you can see it's improving and getting a better fit to cos 2x, and if I go on and on looking at even values of n, we get a better and better fit. If I stop at n equals 20, you can see that this polynomial is an extremely good approximation, certainly from minus pi to plus pi. It's a good approximation for cos 2x. In the next video, we're going to be looking at the Maclaurin series of standard functions.